Hello friends, continuing with the topic of electric potential, today we take up electric potential due to an electric dipole. Previously we have seen that electric potential due to a point electric charge at a distance r from it is equal to K naught Q by R, and due to multiple charges at a given point is equal to algebraic sum of the electric potential due to each charge. Okay, and now today we take up electric potential due to an electric dipole which have two charges only, plus Q and minus Q. Now let us see how it comes out to be a physical situation. Consider an electric dipole consisting of two charges plus minus Q, separated by a distance 2a, such that its electric dipole moment P is equal to Q into 2a. Now let P be any point with position vector r from midpoint of the dipole. Let r1 be the position vector of point P from plus Q and r2 be the position vector from minus Q as shown in diagram. Now at the second step we go for electric potential at P due to plus Q. Say V plus, it is equal to K naught Q by R1. And at the third step we go to electric potential at P due to minus Q. Say V minus equal to K naught minus Q by R2. Now at the fourth step we calculate electric potential at P due to electric dipole. Since we know electric potential at a given point due to multiple charges is equal to algebraic sum, therefore if V is the electric potential at P, then V is equal to V plus V minus. Okay, algebraic sum we take V plus and V minus, or we can write V is equal to K naught Q by R1 minus K naught Q by R2. We substitute the value of V plus and V minus, or we have V is equal to K naught Q, we take out common, within bracket 1 by R1 minus 1 by R2. Let us mark it as equation 1. Now at fifth step let us calculate 1 by R1 minus 1 by R2. Consider triangle CAP. According to triangle law of vectors, we have vector A plus vector R1 is equal to vector R, or R1 vector R1 is equal to vector R minus vector A. And now we are to calculate magnitude of R1. We write here R1 square is equal to R square plus A square minus 2AR cos theta. Let us mark it as equation 2. Now since R is very large as compared to A, therefore A square in equation 2 can be neglected. After neglecting A square, we are left with R1 square is equal to R square minus 2AR cos theta, or it is equal to R square into 1 minus 2A cos theta by R, bracket closed, or R1 is equal to R into 1 minus 2A cos theta divided by R whole power half. After taking square root, we are left with R1 is equal to R into within bracket 1 minus 2A cos theta by R, bracket closed, raised to power 1 by 2. Or we can write it as 1 by r1 is equal to 1 by r into 1 minus 2a cos theta by r raised to power minus 1 by 2 after taking reciprocal of r1. So we have this expression. Now using binomial, when we use binomial, the power comes inside with the second term. Okay, so when minus 1 by 2 comes inside the bracket with the second term, 2 cancels and minus becomes plus. Therefore, using binomial expansion, we have 1 by r1 is equal to 1 by r into 1 plus a cos theta by r. Let us mark it as equation 3. Now similarly, considering triangle BCP, we have 1 by r2 is equal to 1 by r into 1 minus a cos theta by r. Let us mark it as equation 4. Now subtracting equation 4 from equation 3, we get 1 by r1 minus 1 by r2 is equal to 1 by r into 1 plus a cos theta by r bracket closed minus 1 by r into 1 minus a cos theta by r bracket closed, and it is equal to 2a cos theta by r square. Let us mark it as equation 5. Now substituting the value of 1 by r1 minus 1 by r2 from equation 5 in equation 1, we get V equal to k naught q into 2a cos theta by r square, or it is equal to k naught p cos theta by r square, because 2qa is equal to p, because p is equal to q into 2a. So we, in place of q into 2a, we write here p, electric dipole moment. Okay, or we can write it as k naught p dot r cap divided by r square. Thus, electric potential due to an electric dipole at any point p with position vector r from midpoint is given by the expression V is equal to k naught p dot r divided by r square. I repeat, electric potential due to an electric dipole at any point p with position vector r is given by the expression V is equal to k naught into p dot r cap divided by r square. Okay, let us mark it as equation 6. And now discussion. First point, electric potential at every point on the circumference of the cone formed by the position vector around the axis of the dipole remains the same and is given by the expression V is equal to k naught p dot r cap divided by r square, and it is equal to k naught p cos theta by r square. Okay. Second point, when theta is 0, so look at the formula along with, only then you will understand. When theta is 0, V on axis of the dipole is given by V is equal to k naught p by r square. When theta becomes 0, the point P comes on axis of the dipole, and at the axis of the dipole, electric potential V will be equal to k naught p by r square. Third point, when theta is pi by 2, the point lies at the equator, and then V becomes 0. So at every point on equatorial line, electric potential due to the dipole is 0. Okay. Now fourth point, we look at the formula and see that the electric potential due to dipole is inversely proportional to R square. But in case of point electric charge, electric potential is inversely proportional to R only. You have to mark this difference. Okay. So in case of electric dipole, electric potential is inversely proportional to R square, and in case of point electric charge, it is inversely proportional to R. Now assignment 2.1 continued. Question number 12. Derive an expression for the electric potential due to an electric dipole at any point P whose position vector R is inclined at an angle theta with the dipole axis. Okay, is the article, the whole article you have to explain. Question number 13. What is the electric potential due to an electric dipole at an equatorial point? Is it essential that where electric potential is 0, electric field must be 0? Okay, you answer this question, and this assignment is continued to next slide. Let us see how it is. Now question number 14. The following data was obtained for dependence of the magnitude of electric field with distance from a reference point O within the charge distribution in the shaded region. So here you look at the diagram. This is the shaded region. Here is the shaded region. Now questions. A part. Identify the charge distribution and justify your answer. B. If potential due to this charge distribution has value V at point A, what is the value at point A dash? So this is point A and this is point A dash. So point A lies on axial line and point A dash lies on equatorial line. And this data is given to you, and you assess the data, understand the data, and try to answer it. Question number 15. Two charges minus q and plus q are located at points 0, 0, minus a and 0, 0, a respectively. What is the electrostatic potential at point 0, 0, z and xy 0? So this is A part. B part. Obtain the dependence of potential on the distance of r of a point from the origin when r by a is very large as compared to 1. C. How much work is done in moving a small test charge from the point 500 to point -700 along the x-axis? Does the answer change if the path of the test charge between the same points is not along the x-axis? So this is all about electric potentials due to an electric dipole at any point P with position vector r inclined at an angle theta with dipole axis. Okay, to solve these questions on the basis of the text that you have learnt. Thank you so much. God bless you. Next time we'll take up the third part of this topic, electrical potential difference. Till then, goodbye.